The committee inside the machine. An introduction to mixture of expert. When DeepSeek released its R1 reasoning model in January 2025, the reaction went far beyond the usual excitement surrounding a new AI model. The surprise was not simply that a Chinese AI company had produced a highly capable reasoning system. It was that DeepSeek appeared to have achieved frontier-level performance, while using substantially fewer computational resources than many observers had assumed necessary. However, the numbers require some care. The widely repeated figure of roughly $6 million did not represent the total cost of developing DeepSeek R1. It came from DeepSeek's earlier V3 technical report, which estimated that the complete training run for DeepSeek V3, including pre-training, context extension, and post-training, required 2.788 million NVIDIA H800 GPU hours, valued at about $5.576 million using an assumed rental cost of $2 per GPU hour. DeepSeek R1 was subsequently developed on top of DeepSeek V3 base using reinforcement learning and additional post-training. Even with those qualifications, the market reaction was extraordinary. On January 27, 2025, NVIDIA's shares fell about 17%, erasing roughly $593 billion in market value in a single trading session. Meanwhile, DeepSeek's AI assistant overtook ChatGPT at the top of Apple's US App Store. For a technology industry accustomed to equating AI progress with ever larger clusters of increasingly expensive GPUs, DeepSeek raised an uncomfortable question. What if better engineering or programming could substitute for at least some brute force scaling? The answer was not one technological trick. Rather, DeepSeek combines several innovations. These innovations include low-precision FP8 training, multi-head latent attention to reduce memory demands, carefully optimized communication among GPUs, and a training system designed to overlap computation with communication. But at the architectural center of DeepSeek V3 and R1 was an increasingly important idea: mixture of experts. A conventional dense neural network uses essentially the same set of model parameters to process every token. Whether the model is explaining the capital of France, debugging Python code, solving an algebra problem, or summarizing a legal contract, every token passes through the same dense network components. This is powerful, but computationally expensive. Imagine a hospital where every patient, someone with a sprained ankle, someone having a heart attack, and someone suffering from hay fever, must be examined simultaneously by every doctor in the building. The hospital would certainly have enormous medical expertise available, but it would be an absurdly inefficient way to deliver care. Mixture of experts introduces something like a triage desk. Instead of relying on one enormous feed-forward network, an MO layer contains many smaller feed-forward networks called experts. A lightweight routing mechanism examines each token and decides which small subset of experts should process it. Only those selected experts perform the main computation for that token, the others remain inactive for that particular routing decision. The result is a form of conditional computation. The model can contain an enormous amount of parameter capacity without activating all of it every time it produces a token. This principle has been central to modern sparse mixture of experts research since Google's sparsely gated mixture of experts work in 2017 and later systems such as the switch transformer. DeepSeek V3 illustrates the idea at remarkable scale. Most of its mixture of experts layers contain 256 routed experts plus one shared expert, but only 8 routed experts are selected for each token. Across the model as a whole, DeepSeek V3 contains 671 billion parameters while activating approximately 37 billion for each token. In other words, the model has access to a parameter pool roughly 18 times larger than the number of parameters actively used at any one time. That does not mean DeepSeek performs only 5.5% of the work of an equivalent dense model. Attention layers, shared experts, routing, memory access, and communication still consume resources. But it illustrates the central advantage of mixture of experts. Model capacity can grow much faster than the amount of computation required for each token. One of the clearest real-world examples comes not from chatbots but from machine translation. Building a translation system for a handful of major languages is relatively straightforward because enormous quantities of training text are available. The problem becomes much harder when one system must handle hundreds of languages, especially languages for which relatively little digital text exists. Meta's No Language Left Behind, NLLB 200, project was designed to address exactly this problem. The system translates 200 languages, including many low-resource languages that were poorly served by conventional translation technologies. Rather than building hundreds of completely independent translation models, Meta used a sparse mixture of experts architecture with both shared and specialized capacity. Low-resource languages could draw on shared capacity instead of having to support an entire model from their limited training data. Meta has subsequently applied techniques developed through the NLLB project to improve translation systems used on Facebook and Instagram. This example reveals why mixture of experts is more than a clever way of reducing a GPU bill. It allows one large system to accommodate many different patterns of data while selectively allocating computation where it is useful. But what does an expert actually know? The word expert creates a potentially misleading mental picture. It is tempting to imagine that a mixture of experts model contains a mathematics expert, a French expert, a programming expert, a poetry expert, and perhaps a legal expert. And that the router simply sends each question to the appropriate specialist. That is generally not how modern Mo language models work. The experts are learned rather than manually assigned. During training, the routing network and expert networks evolve together. Some degree of specialization does emerge. Artificial intelligence researchers can observe different experts receiving different amounts and types of data. DeepSeek's own experiments found stronger expert specialization patterns under its load balancing method. But the boundaries are not necessarily categories that humans would naturally invent. Experts may respond to overlapping combinations of linguistic structure, domains, token patterns, context, or other features embedded deep within the model's internal representation. So it would be misleading to open the model and expect to find expert 47, cardiology, and expert 193, Shakespeare. Their specialties simply do not have to correspond neatly to ours. That distinction is important because mixture of experts is not the same thing as a multi-agent AI system in which one explicitly assigns different agents different jobs. In mixture of experts, routing occurs inside the neural network, often token by token and layer by layer, at a level largely invisible to the user. The attraction of mixture of experts becomes clearer when we consider the economics of scaling AI. In a dense model, increasing the number of parameters generally increases the amount of computation required during training and inference, because the same large parameter set participates in processing every input. Sparse mixture of experts architectures weaken that relationship. The total parameter count can grow substantially while the number of parameters activated for each token remains much smaller. Put differently, total parameters contribute to capacity. Active parameters are more closely related to the computation required for a particular token. That distinction is why mixture of experts has become so attractive to developers trying to build very large models without increasing computational requirements at the same rate. The idea itself is much older than the current AI boom. Robert Jacobs, Michael Jordan, Stephen Nowlin, and Geoffrey Hinton introduced adaptive mixtures of local experts in 1991. Noam Shazir and colleagues brought sparse mixture of experts into large-scale neural language modeling in 2017. Google subsequently developed G-Shard and the switch transformer, and Mistral demonstrated the approach again with Mixtral. DeepSeek then pushed sparse expert architectures to much larger scales. Mixture of experts is now unmistakably part of mainstream frontier model design. Besides DeepSeek, Alibaba's Qwen family also includes large mixture of experts models. And Meta adopted mixture of experts for Llama 4 after deliberately retaining a dense architecture for Llama 3.1. That last example is revealing. Mixture of experts has substantial advantages, but dense models have not become obsolete. Different architectures make different trade-offs. The efficiency of mixture of experts does not come free. One of the hardest problems is load balancing. If the router discovers that a particular expert performs slightly better early in training, it may start sending that expert more tokens. The expert consequently receives more training, improves further, and becomes even more attractive to the router. Eventually, a small number of experts may become overloaded while others receive too little training. Traditional mixture of experts systems address this problem partly through auxiliary loss functions that encourage the router to distribute tokens more evenly. But forcing experts to receive artificially balanced workloads can conflict with the model's primary objective of learning the best possible prediction. DeepSeek introduced an important refinement, an auxiliary loss-free load balancing strategy that dynamically adjusts per expert bias terms to encourage balanced routing while reducing interference with the main optimization objective. DeepSeek also uses fine-grained routed experts and shared experts so that common knowledge does not have to be replicated independently across every specialist. Yet other costs remain. Sparsity saves computation more readily than it saves model storage. The enormous pool of expert parameters still has to reside somewhere in the system. Experts distributed across many GPUs must exchange tokens through high-speed interconnects, creating an all-to-all communication problem. As models scale, moving information among GPUs can become as important as the arithmetic performed by the GPUs themselves. This is why mixture of experts models can be computationally efficient yet operationally demanding. DeepSeek itself notes that the recommended deployment unit for DeepSeek v3 is relatively large and can be burdensome for smaller organizations. Earlier mixture of experts research likewise identified communication cost and training instability as major obstacles. In short, mixture of experts does not make hardware irrelevant. It changes which hardware resources become bottlenecks. This brings us back to the panic that followed DeepSeek's arrival. At first glance, a more efficient model architecture seems threatening to GPU manufacturers. If an AI system can achieve more with fewer computational operations, shouldn't the world need fewer GPUs? Not really. The Jevons paradox describes situations in which improvements in the efficiency of using a resource reduce its effective cost so much that consumption of the resource ultimately increases rather than decreases. Applied to AI, the argument is straightforward. If architectural improvements make each AI query dramatically cheaper, companies may deploy AI in far more applications, users may make many more queries, and developers may build systems that perform vastly more inference. Under those conditions, lower compute requirements per task could coexist with higher total demand for compute. Whether the rebound exceeds the efficiency gain depends on how strongly AI usage responds to falling costs. That is why the apparent choice between better algorithms and more powerful hardware is probably a false one. DeepSeek did not demonstrate that clever algorithms can replace GPUs. It demonstrated that algorithm design, model architecture, numerical precision, memory management, communications engineering, and hardware must increasingly be optimized together. Mixture of experts captures that shift beautifully. Instead of asking every part of an enormous model to solve every problem, it asks a smaller question: who needs to work on this token? The answer can save enormous amounts of computation, but only if the router chooses well, the experts learn useful divisions of labor, and the hardware can move the resulting information quickly enough. Perhaps that is the more consequential lesson of mixture of experts. The future of artificial intelligence may not belong simply to the model with the most parameters or the company with the most GPUs. It may belong to the systems that are best at deciding which resources to use, when to use them, and when to leave the rest alone. What do you think? As artificial intelligence continues to scale, where will the bigger breakthroughs come from? More powerful hardware, more efficient architectures such as mixture of experts, or better integration of the two? And will greater efficiency ultimately reduce the demand for GPUs, or simply make AI cheap enough that we use far more of them? I'd be interested to hear your thoughts in the comments. Thank you for watching. Goodbye.